All right. Hello, everyone out there in physics land. It's today again. So it means it must be time for more AP Physics C mechanics. Now, today we're going to talk not so much about Newton's third law, but an application of it, which is how do we deal with forces when there are multiple objects in a system, right? Now, this entire discussion is going to overlap with Physics 1. So if you want to tell your Physics 1 friends that this applies to them too, it's all good. Okay, couple of things before I go on to the warm-up. This particular presentation, I don't think I have any nifty little animations other than my timers, but I've been getting a lot of contacts from folks who are like, hey, how do you make a little nifty animations? And so I'm just going to briefly talk about that. They're all animated GIFs or GIFs, however you're supposed to say it. GIF to me is a peanut butter, right? And so back in the 90s, I used to write video games for like DOS computers, right? That tells you how old I am. I'm sure I look that old, right? And so I still have all the code from those days. And so what I did is I just wrote a little code that would output animated GIFs rather than output, video game animations to screen. And so I just write for each animation you see, I just write a little code and it generates each of the individual frames and assembles them into an animated GIF in case you honestly care. Okay, my name is John Frensley. I teach Prosper High School, Prosper, Texas. You probably know that already. So let's go here to a warm-up. So this is going to be a really basic situation where you have three objects. In this case, you have three carts, A, B, and C. A has a mass of 5 kilograms in the back. B has a mass of 7 kilograms in the middle. C has 3 kilograms in the front, and C is being pulled to the right by a 30 Newton tension. So I'm going to give you 2 minutes, and the question is, what is the acceleration of the system of carts? What is the tension in the ropes? 1, which is between the 5 and 7, and 2, between the 7 and 3 kilogram carts. So let's see if you can get this. Now, I can do it in my head. This is what I want to teach you today. Can you do it in your head, or do you have to write it out? All right, on your mark, get set, think. Seemed really long for 2 minutes, honestly. I'm going to go over the answer in a little bit, so just sit tight. But like I said, it's probably best if you have some pencil paper, something to write with to kind of try and work these out on your own during the times when the timer's on the screen. Remember, the timer's on the screen, the music's playing, and you don't like the music, then just hit mute until the timer's up, and I'm going to start talking. Okay, so here's what we're going to do. We're just going to apply Newton's second law to systems of objects. Now, I know what you're thinking, but wait a minute, this is called Newton's third law. Yes, that's true, but when we have systems of objects, we're really using Newton's second and third law at the same time. So I'm going to talk about where Newton's third law comes up, but mostly the centerpiece is Newton's second law when we deal with forces and accelerations and things like that. We're going to look at a train of blocks like the warm-up you just saw. We're going to look at systems with pulleys. Okay, so can you think of situations where you have 2 or 3 objects that are connected together, usually by ropes? How does Newton's third law play into that? But really, how are we going to use Newton's second law to analyze those situations, right? Here's what you need to know. If I could say Newton's second law, I know what you're thinking. Force equals ma. Well, really, you don't say force equals ma because there's no such thing as one force, right? Only an object in free fall has one force acting on it. Everything else has more than one force. So I don't say force equals ma. I might say net force equals ma. And here's a programming note for you teachers out there who are paying attention. My New Year's resolution for this school year was to be very careful about when I use the word net and when I use the word total. So I'm trying to only use the word total whenever I'm talking about adding up numbers that can only be positive. For example, total mass, right? But I want to say net anytime I'm trying to signal my students that some of the numbers that they're adding up might be negative, right? So I will say net force, net momentum, net charge. And I tell students when they get net, and I'll talk to them, I'll say, you know, when I get paid, I'm told that I'm getting paid X amount of money, but the paycheck is actually less because I had money taken out for taxes and insurance and things like that. So that's my net pay. What does net mean? It means the positive minus some negatives or plus some negatives. You just don't want to double over that negative. So Newton's second law, net force equals ma. Well, how do I say net force? I say the net force is all the forces that are in the same direction as acceleration minus all the forces that are opposite the acceleration. So knowing the direction of acceleration is going to matter when we talk about these force problems, right? That equals the object's mass times the object's acceleration. What if we have a system of objects instead? Well, if you have a system of objects, it's almost the same equation, except now I'm going to look at the external forces on the system that are in the same direction as acceleration. What's an external force? Well, let's first talk about what a force is to begin with. A force is one object pushing or pulling another object. The object that's doing the pushing or pulling, we call the agent of the force, and the object that's being pushed or pulled, that's the object of the force. The agent is doing the pushing or pulling, the object is being pushed or pulled. If the agent and the object are both in your system, that's an internal force, and internal forces cannot affect the acceleration of your system. So if the agent and the object are both things that are within your system, then that is an action reaction pair, and that, you know, agent pushes object, object pushes agent with equal and opposite force cannot in the net affect your acceleration. But external forces, or the agent is not part of your system, right? So if the agent is outside your system, then the force is external. If that force helps acceleration, we're going to count it as positive. If that force is against acceleration, we're going to count it as negative. But this is the key. Look at the total system's mass. Look at the system's total mass. So the whole system's mass has to be accounted for, not just part of it. All right. And then times the acceleration of everybody in the system, right? So that's what I'm going to be emphasizing today is this screen, which I just got rid of. So we're going to apply these to 4 examples: the warm-up, the horizontal train of blocks. Then we're going to take the train of blocks, we're going to pull it upward or lower it downward, right? So I call that a vertical train. Then an Atwood machine, it's 2 objects that are connected by a pulley. Then a modified Atwood is where one of the objects might be on an incline or on a table or whatever. Today, they're going to be on a table, right? So let's look at your horizontal train of blocks that you did for a warm-up, right? So here's what you could do. What you could do is you could draw a free body diagram for each individual car. And if you draw a free body diagram for each individual car, you can come up with a Newton's second law equation for each individual car. So remember what I'm trying to find. I'm trying to find the acceleration and each of the 2 tensions. So let's start with car A. So car A, I have force tension 1, and then the other forces, normal and weight, cancel, right? So force tension 1 is the only force that helps the acceleration, which is to the right. There's no leftward force on car A, so force tension 1 equals ma. I mean, this is a true equation, but there's a problem with it. I don't know the number for force tension 1. I don't know the number for acceleration. You have an equation with 2 unknowns. That's something you can't get numbers for. You can't solve it, right? So let's look at B, for example. Okay, so let's look at car B. Well, car B has force tension 1 pulling it back. So there's your action reaction pair. Mass A is being pulled forward by mass B using force tension 1. Cart B is being pulled backward by cart A with the same force tension 1. So force tension 1 is B pulls forward on A pulls backward on B, same force, opposite direction. And force tension 2 is helping B go forward. So here's an equation for that. Tension 2 helps B go. Tension 1 holds B back equals B's mass times acceleration. Now I got 3 things I don't know in this equation. I don't know either of the 2 tensions or the acceleration. Boo. Okay, let's look. Maybe the answer is with cart A. Maybe cart A can help me figure something out. Okay, well, here's the Freebody diagram for cart A. You notice I'm trying to color code the forces here, right? Where the yellow force tension 2 here is the same as the yellow force tension 2 back here on the previous slide. Action reaction pair. B pulls backwards on C. C pulls forward on B using the same force tension 2. So force tension 3, which I know that's 30 newtons. So rope 3 is being pulled forward with 30 newtons. You see that there? So I do know that, but I don't know force tension 2. I don't know the acceleration. So great, I've got 3 equations and 3 unknowns. You could solve that using elimination and like a system of equations, or you could not do that and maybe do something a little bit smarter, which is what I want to teach you today. So what could you do? You could combine the carts together into systems, right? So instead of looking at A and B separately, let's treat them as one combined thing. So the one combined thing would have combined force normal up, combined mg down, and force tension 2 to the right. Notice force tension 1 is now internal to the system because the agent and the object for force tension 1 are both in the system. A pulls B, B pulls A, both A and B are in the system. So force tension 1 is not something we draw in our free body diagram. So I could say this. I could say force tension 2 is mass A plus mass B times acceleration. Well, that's still 2 unknowns. I don't know force tension 2, and I don't know acceleration. So maybe I can try the system of B and C, right? So what does B and C have? Well, B and C has tension 1 pulling back. What is tension 1? A pulls on B, but A is not part of the B and C system. So now that's an external force. Tension 3 comes from who knows what. I can't see off the screen there. Something else is pulling tension 3. That's not part of the system. So I get tension 3, which I know 30 newtons, and tension 1 minus tension 1, which I don't know, equals the 2 masses combined times acceleration. So this is still not a good equation for me. So what equation is going to get me the acceleration? Here's a key point for today. So listen carefully. In order to get the acceleration, look at the entire system as a whole. In other words, look at all 3 carts as if they were one thing. So if someone comes up to me and says, here's 18 blocks all connected together, I'm pulling them with 1,000 Newton force, how much is the acceleration? I'm not going to think 18 carts. I'm going to think one combined cart. So if I combine all of the carts together, then there's really only one external force. The other 2 balance out, the normals and weights balance out. So again, I'm looking for forces that are external and unbalanced. They have to be both external and unbalanced, right? So I've got force tension 3, a number I know, equals the sum of the masses, a number I know, times acceleration. So if force tension 3 is 30, and the sum of the masses is 15, then the acceleration was 2. So hopefully you were able to do that in your head. Hopefully you just said, wait a minute, I'm not going to look at 5 and 7 and 3. I'm going to look at 15 kilograms. You're pulling 30 newtons on 15 kilograms. That's an acceleration of 2 meters per second squared. Okay, so a problem can be easy or difficult based on which system you choose and consider for each part of the problem. So for the acceleration, I look at the system as a whole. So I've got my 30 newtons pulling tension 3, my total mass of 15. There's my acceleration 2. If you got that in your head, give yourself a pat on the head. Good job. Okay. Now, how am I going to get tension 1 and tension 2? I always start from the back of the train. So in other words, I'm going to look to get tension 1, I'm going to look at everything that's behind tension 1. So what was behind tension 1? Well, if you go back to this diagram, what was behind tension 1 was just mass A. So I'm going to look only at the system consisting of mass A. And just so you know, when I look at tension 2, I'm going to look at everything behind tension 2. So in my mind, tension 1 is pulling 5 kilograms. Tension 2 is pulling 12 kilograms. So I come up here and I say tension 1 is pulling just A. I know the acceleration, so the mass of A is 5, the acceleration is 2, tension 1 is 10 newtons. All good, all right? Not that difficult. To find tension 2, I'm going to look at everything behind tension 2. So everything behind tension 2 is 12 kilograms. 12 kilograms are accelerating at 2 meters per second squared. Notice, once you get the acceleration, that's everybody's acceleration. Everybody has the same acceleration, okay? So we're just plugging in 2 for the acceleration all the time. So I get my 24 newtons. So, and notice, this is important. Each rope, as you get to the front of the train, has greater tension. The last rope is the least tension because he's only pulling what's behind him. The next rope has more tension because he's pulling everybody behind him. Then the next rope, even more tension, pulling everybody behind it. Doesn't matter what the individual masses are because you're pulling mass, you're pulling more mass, you're pulling more mass, you're pulling more mass. That would be a perfect question to ask, especially on a P1 exam, possibly on a Physics C exam. Remember, your exams this year are text only, so you're only going to be asked conceptual type questions. Yeah, so that would be a good concept to know. So what you just saw is that we looked at the whole system to get the acceleration. That's important. Then to solve for individual forces within the system, we changed the system to be less. To look for the acceleration of the whole system, we looked at the whole system. But to get the acceleration of tension 1, we reduced the system to something tension 1 was pulling. To get tension 2, we reduce the system to something only tension 2 is pulling. So to get tension forces, we reduce the system and only look at part of it, not the whole thing. But step 1, get the acceleration by looking at the entire system. Okay? All right, here's your check for understanding. We're going to take those blocks and we're going to turn them vertically. So we've got tension 1 at the top. We've got it's supporting 3 kilograms. Then underneath that, tension 2 is supporting 5 kilograms, and underneath that, tension 3 is supporting 2 kilograms. Right now, the blocks, I'm going to give you the acceleration already. The acceleration is 5 meters per second squared. Calculate the tension in all 3 ropes. Now, the mistake you're going to make is you're going to forget about the weight force, right? So don't sit here and just say, oh, well, the total mass is 10 kilograms and the acceleration is 5 meters per second squared. So that's 50 newtons, right? No, don't forget that those 10 kilograms have a weight force pulling them down. So that makes this a little bit more difficult than the horizontal train. So you're going to get 3 minutes for this bad boy, okay? So here comes your 3 minutes on your mark, get set, go. that music made you happy. Okay, so let's just look at block A. Okay, so if we look at block A, then we have tension 1 up and tension 2 and mg down. So I can come up with an equation. Tension 1 helps you go. Tension 2 and mg hold you back. So they're both negative equals ma. All right, that's just looking at block A. Let's look at block B. Now block B has okay, so there you go. So block B has tension 2 up and tension 3 down and its own weight down. So we've got tension 2 and tension 3, tension 2 up minus tension 3 down and weight down equals ma. Okay, so why do I not like looking at at block A and block B? I don't like block A and block B because they both have 2 unknowns. So go back and you'll see that tension 1 and tension 2, I don't know. That's an equation with 2 unknowns. Tension 2 and tension 3, I don't know. That's an equation with 2 unknowns. But if I look at the very last block, let's look at the very last block, the one on the bottom, mass block C. That only has 2 forces on it. Tension 3 up minus mass mg down for C equals ma. So you could easily just plug into this equation right here. So let's see if I can do it in my head. So I have 2 times 10, and then I've got 2 times 5, that's the acceleration. So I've got something minus 20 equals 10, so tension 3 would be 30 newtons. Okay. Do I like looking at the A and B system? Let's have a look here. So the A and B system, treated as if it's a single block. Treated as if it's a single block. So the A and B system has tension 1. Look at how it crosses that dotted line boundary, right? So tension 1 crosses, that's how I know that it's an external force. The force actually goes across the boundary, right? So we got tension 1 up, and tension 2 is internal, so I'm not going to draw it. Tension 3 is down, so you see it over here in the diagram, and the 2 weights combine as well. We're treating this as a single 8-kilogram object, right? Well, here's my equation. I've got tension 1 supporting blocks A and B, tension 3 pulling down blocks A and B. You have the weight of blocks A and B pulling down, and the total MA of A and B, but this still has 2 unknowns. The 2 unknowns are tension 1 and tension 3. If you wanted to, you could say, well, you just found out that tension 3 is 30 newtons. Well, yes, you could, and then you could plug that in and get tension 1. But for me, that's too difficult. So instead, I'm going to look at blocks 2 and 3. If I look at blocks 2 and B and C, if I look at blocks B and C together, then treating them as a single object, I've got tension 2 up. I've got their combined 80 newtons down. I'm using G equals 10. I've got 80 newtons down. So this is going to be a very easy equation. I can just say tension 2, which I don't know, minus 80 newtons, 8 kilograms, time, 70. I'm not even looking at this correctly. It's 70 newtons, 7 kilograms. Let me try that again. Tension 2 up, 7 kilograms. I can do math. I swear I can some days. Times 10. So that's 70 newtons equals 7 times the acceleration of 5. So that's 35. So I'm thinking what minus 70 equals 35? This is probably going to be 105 newtons, right? So notice the best systems to analyze for tension 3, everything below tension 3. For tension 2, everything below tension 2. So for tension 1, you know it, everything below tension 1. Each rope is responsible for who's below that rope. Each rope is responsible for who's below that rope. So tension 1 really thinks he's carrying 10 kilograms. Tension 2 thinks he's carrying 7 kilograms. Tension 3 thinks it's attached to 2 kilograms. Do you see how that works? So tension 1 says, I've got to counter all 100 newtons, that's 10 kilograms times 10 meters per second squared, all 100 newtons of downward weight. I've got 10 times acceleration, the 10, so that's going to be 50, right? Because the acceleration is 5 and the total mass is 10. So I've got what minus 100 equals 50. It's going to be 150 newtons. So let me just review. To find tension 3, we look at the bottom block only. We just looked at the bottom block and we got 30 newtons. We're just going over it again. Then, okay, for tension 2, we looked at everything below tension 2, B and C. So we just plugged in the total mass below. It's almost the same equation. It's up force minus weight equals mg. It's just this time it's with 7 kilograms rather than 2. Okay, so we got our 105 newtons. Then for tension 1 at the top, it's the same equation, tension minus weight equals ma, but now we're using the total mass below tension 1, which is all 10 kilograms. Okay, now the rope on top is the most tension, less going down. What if the acceleration were down 5 meters per second instead of up 5 meters per second? I'm going to let you try this on your own, but you're going to find out that the top tension is still the most, less going down. So I'm just going to really quickly tell you what if you said 5 meters per second squared down, you would get, let's see, I think you would get 10 newtons here, and you would get 35 newtons here, and this last one you get 50 newtons, right? So you get 10, 35, and 50 newtons for the three tensions, still the most at the top, then going down. Try it on your own and see if that's what you get. Okay, let's talk about an Atwood machine and pulleys. Okay, so the job of a pulley is just to change the direction of the tension force. Okay, now there's ideal pulleys and then there's not so much, right? So what's an ideal pulley? An ideal pulley is the pulley has so little mass that we can ignore the mass, much less than what the pulley is connected to. And the pulley has such low friction on its axle that we can pretend like there's no friction. So you might call it an ideal pulley or a massless frictionless pulley. What makes a pulley ideal is that if the pulley is ideal, no mass, no friction, then the tension is the same on both sides of the rope. It's the same rope, but the tension is the same number of newtons on both ends if the pulley is ideal. If the pulley has either mass or friction, then the two tensions on the two ends are different, and we have to bring in some rotation concepts. And I'm going to do a little bit of preview of that today, so hold tight, okay? Hold on to your butts. Okay, so Atwood machine is basically a pulley wheel with a string that passes over it, two objects and hang at the end. So this thing down here is called an Atwood machine. This thing over on the right is called a modified Atwood machine. That just means that there's a ramp or a table that one of the blocks is on, which could have friction. Now remember, if the block has friction, that does not prevent the pulley from being ideal. If the pulley itself has friction, then the tensions are different on both ends of the rope. But as long as the pulley has very low mass, very low friction, the whole rope has the same tension both ends. All right, so let's talk here. What if I told you I could do this problem in my head? Seriously, in my head, I could look and then say, hey, 13 kilograms and 7 kilograms with ideal pulley. What's the acceleration? What's the tension? Like, I could theoretically just do this in my head. Well, that means there must be a trick to this. So here's your job. I'm going to give you 3 minutes. If you know the trick, make it happen. If you don't know the trick, then write it out. So what are you going to do? You're going to do a free body diagram for the 13 and for the 7. You're going to come up with an equation for the 13 and an equation for the 7. Then you might have to solve using systems or elimination or something like that. So see what you can come up with in 3 minutes. 2 free body diagrams, 2 force equations, 1 for each block. Can you turn them into one equation that gets you the acceleration? Then do something, get the tension. 3 minutes, go. that's enough of that. All right, so the answer is what? 3 meters per second squared. I'm telling you, I can do this in my head. So let me tell you the long way to do this, and I'm going to tell you the quick way to do it, right? So I'm going to draw, first of all, please, let's agree that the heavier mass is going to be, the 13 is going to accelerate down, the 7 is going to accelerate up. Okay, let's just get that across. Okay, so let's do a free body diagram for the 13. So the 13 is going to have its mg down, its force tension up. Notice the mg is longer than the tension because it's going to accelerate down. I also draw acceleration to the side. It's not a force, but it's going to help me out, so I draw it to the side. Okay, the 7 is going to have the same force tension. It's an ideal pulley, same force tension up, but its acceleration is going to be up. So the force tension is better than the mg down. Okay, so there you go. Now, what am I thinking about? I want to come up with an equation for each of these, right? So for each free body diagram, we can make an equation for Newton's second law. So for the 13, we've got the mg helps the acceleration. The force tensions against the acceleration equals ma. For the little one, we have force tension helping acceleration. Its weight is opposing, so minus its weight equals ma. Notice I'm using capital M for 13 and lowercase m for 7. On the AP exam, when you type, please try to use the correct upper or lowercase for whatever letter you're talking about. Please do not turn on caps lock, okay? Get your shift ability in gear, right? Okay, so let's see. So what do I want to say now? I want to take my equation for 13. I want to take my equation for the 7. Look at that. There's my equation for 13 and my equation for the 7. I've got 2 equations and 2 unknowns. My 2 unknowns, I don't know the acceleration. I don't know the tension. I definitely know all the m's and g's, but I don't know the acceleration, don't know the tension. So I'm going to do this thing in math called elimination. So what do you do when you eliminate, right? What you do is you just add everything on the left and you add everything on the right to make one new equation. So we're going to use elimination to solve for the acceleration. So here we go. Here's my 2 equations, okay? Now I'm going to eliminate. So what's that going to look like? I'm going to have mg minus force tension plus force tension minus little mg. So that's just all 4 terms with the signs that they had all added together. On the right-hand side, big MA, little ma, add them together. Now, you're probably thinking, you're probably screaming at your computer screen, the tension cancels out, the tension cancels out. That's the key here. The tension, which is internal, it's 13 pulling on 7 and 7 pulling back on 13. The tension, which is internal, cancels out. This only works if the positive force is in the direction of acceleration and the negative force is against the acceleration. So you might come back and say, wait a minute, Frensley, back on this screen, you made down positive and up negative. Shouldn't you always make up positive? And my answer is no, I do not always make up positive. I make the direction of acceleration positive. So if acceleration's down, then down is positive. Let me just tell you right now, that eliminates so much difficult math in your life. So for the 13, I make down positive, up negative. For the 7, I make up positive, down negative, because that's the direction of the acceleration. So I nuke the tensions, and now I've got one variable. I know the 2 mg's, and now I can get the acceleration. So this is what I did in my head. In my head, I just did this. I just did 130 minus 70 for a net force of 60 newtons and a total mass of 20. So how was I able to come up with 3 meters per second squared so quickly? I just looked at this and I said 130 newtons minus 70 newtons. The net force is 60 newtons. The total mass is 20 newtons. F equals ma. And so with my F equals ma, I get 3 meters per second squared. Let me tell you right now, you can jump straight to that step. You don't have to go through the process of looking at each object individually and drawing free body diagrams and writing equations for each one. You can go directly to the big mg minus the little mg equals a total mass times acceleration. How can you construct that equation without having to go through all those motions? Here's all you do. You just say in your mind, big mg is what's making this thing want to go. The 13 kilograms mass wants to make this thing happen. But the 7 kilograms weight does not want this to happen. Weight of 7 does not want that 7 to go up. So the big mg is what's making the system want to do this, but the little mg does not want the system to do this. So big mg is helping us accelerate, positive. Little mg is opposing that acceleration, negative, equals ma. The m has to be the total mass of everything in your system. So the tension's internal. There's no tension in that equation. So we just say the force helping the system go is the big mg. The force holding the system back is the little mg. The whole system's mass, do not just plug in one mass, plug in everyone moving times the acceleration. You can just do that in your head. Okay, so now how do we find the tension force? You can't look at the whole system. You have to choose one of them. So to get the tension force, you just make a choice. I don't care which one you choose, 13 or 7. I chose, okay, I'm going to choose 7 now. So I'm going to look at the 7 and I'm going to say, okay, I know the acceleration is 3. The 7 has tension up and 70 newtons down. So tension up minus 70 newtons down equals ma for the 7, and the 7 only. I'm only looking at the 7, just 7, 7, 7, 7, 7, 7. Okay, not the whole thing, right? I look at the whole thing for the acceleration, but just the 7 or the 13 for the for just the tension. Maybe I'm thinking 13 is unlucky. Who knows? Isn't today the 13th? No, it's the 10th. 13th is Monday. Okay, so then I get 81 newtons, right? Okay, and maybe you could do that in your head if you really wanted to, but you know, that's a little bit more complicated. To get the tension, you look at one object only. Now, I want to just review what we learned about a massless Atwood machine and then go to one that actually has mass. So I'm going to go through this a little quickly. You might have to pause and review if you're on the replay, right? So you'll see that I drew the forces on each block here. All good. You're going to create a Newton second law equation for the big block. Its weight minus tension equals ma. For the small block, its tension minus mg equals ma, and you're going to use elimination and you're going to solve for acceleration. We just did that. What if the pulley now has mass? If the pulley has mass, then look, and I hope you can see this right now, you can see that the tension on the left and the tension on the right are different amounts of tension. We have to now use torques on the pulley. So the little block, or the big block, has the same equation that it had before, and the little block has the same equation it had before. It's just now it's force tension left and force tension right, which are not the same tension. The pulley, I have to use torques. Look, this is a torque, radius times force minus radius times force. Those are two torques. Why is FTL positive? Because FTL is what's getting the pulley to rotate counterclockwise. FTR does not want the pulley to rotate counterclockwise, so it's an opposing torque. The torque that helps you rotate minus the torque that's against your rotation equals I alpha. Well, what do I do in this case, Frensley? Well, look what I'm doing here. I'm going to take the Pulleys equation, and I'm going to replace alpha with a linear acceleration over r. Then I'm going to divide everybody by r again. See, these r's don't cancel, they get worse. So divide each term by r, so this now becomes r squared. So this is a different way of writing the Pulleys equation. So I've got the two block equations and the pulley equation. Okay, and you notice I regrouped the r squared under the I. I can just move the r squared. It has to stay in the denominator, but it's under the I. So here's my big block, little block, and pulley equation. My big block, my little block, my pulley equation. My big block, my little block, my pulley equation. Time for elimination. So let's do some elimination. If you do elimination, you'll see that the big M and little mg's survive the elimination, but all the tensions cancel out. We get almost the same thing we got before. Big mg helps everyone go. Little mg holds everyone back. But look at what we have. We don't just have the big and little m, but we have additional inertia from the pulley. So what do the massless pulley and the massive pulley have in common? They have the same net force, big mg minus little mg, and they are divided by their total amounts of inertia. For a massless pulley, the only inertia, which is the mass of the blocks, just comes from the blocks. But for a massive pulley, the forces are the same, but we have additional inertia from the pulley. And please note, I over r squared is a number of kilograms. I over r squared is the number of kilograms of inertia that the pulley adds to reduce the acceleration. Okay, we're going to do one more. It's going to be a modified Atwood. So again, this is one you might be able to do in your head. That'd be great. If not, you need to do a Freebody diagram for the 5 and make an equation. Freebody diagram for the 10, make an equation. Watch out, there's friction. Okay, then you need to do elimination. The pulley is ideal, but the table is not. So do elimination, see if you can solve for the acceleration and the friction and the tension force, and you get 3 minutes on your mark and set, go. Time is up. We're going to go through this a little bit quickly. I hope you don't mind because we're running out of time here. So let's start with agreeing that the 5 kilogram accelerates down and the 10 kilograms is going to accelerate to the right. Here's the Freebody diagram for the 10 kilogram. It's got more tension than friction, or else it would not accelerate. So I'm going to say also that the 5 has more weight than tension, right? These two tensions are the same. This tension 10 pulls backward on 5. This tension 5 pulls forward on 10. So I'm going to change. Notice I changed the friction into mu force normal. And the force normal, if you're on a flat with no other vertical forces, is equal to mg. So I'm going to come up with an equation for the 10. It's going to be the tension helps the acceleration minus the friction mu mg holds back on the acceleration against the acceleration equals ma. For the red, I'm going to say that the little mg helps it accelerate. The force tension holds it back equals ma. So now let's just do elimination with these, right? So I'm going to do elimination. I'm just going to say tension minus mu mg equals ma. Mg minus tension equals a little ma, right? I'm going to do my elimination. The tension eliminates. So what do I get? I get the force that helps us all go. The force that's helping us all go is 50 newtons. The force that's holding us all back is the 20 newtons of friction. 50 newtons helps us go. 20 newtons holds us back, and we're all 15 kilograms. So 50 newtons of weight help us go. 20 newtons of friction holds us back equals 15 kilograms times acceleration. Our acceleration is 2 meters second squared. So again, you could have done that in your head if you could only get the mg of the 5, and if you could calculate the friction of this in your head, then you could have said, hey, 50 minus 20, the net force is 30, the total mass is 15, right? Okay, so that's how you would skip straight to that equation. You recognize that little mg helps us go, mu mg holds us back, the tension is internal. So then you would say, okay, the little mg helps us go, the mu big mg holds us back, equals ma. Don't forget the total mass of the system. Don't forget it. Okay, to find the tension force, we have to choose one of the objects and look only at one. In this set of slides, I chose to only look at the 5, but you could just as easily look at the 10. So I said the mg of the 5 minus the tension I'm looking for equals ma of just the 5, not looking at the whole system. And you walk away with 40 newtons. Okay, all good. So what did we learn today? Newton's second law, and I'm sorry for the word wrap on this, but I didn't want to shrink it down really small. Forces that help acceleration minus the forces opposing acceleration equals ma, but the m needs to be the total mass of your system. Look at the entire system and all of its external forces to get the acceleration. Only look at a single object or some inside part of the system in order to get the tension. So if you're asked about tension, don't look at the whole system, reduce it to some part of the system. Don't look at all 3 blocks for tension. Look at 2 or just 1, but look at all 3 blocks for acceleration. Don't look at both blocks from the pulley if you're looking for tension. Just talk about one or the other, but look at both blocks if you're talking about acceleration. Okay, so if you are a Physics 1 student, I have some problems for you that you can look up from the old Physics B exam and from Release Physics 1 exam questions. The ones with stars I think are especially delicious and think that you should do. For Physics C, I have some for you. I'm going to warn you that some of these Physics C ones have rotation rolled in, and I don't know if any of them have calculus. So if you're a Physics 1 student and you want to venture into those, you can, but don't hurt yourself too much on those. But if you're in Physics C, you should also try the Physics 1 ones as well. It'll help you shore up your concepts. It's worth knowing how to do a screenshot. If you're watching the live broadcast right now, I think that Windows machines, you can push a button called print screen and then open either Paint or a Word program and do paste, and then you can see. So like you would hit print screen right now. If you're on a Windows machine, hit print screen right now. Now, if you're on a Chromebook or on an Apple device, you might need to look up on, how do I take a screenshot on a Chromebook, or how do I take a screenshot on whatever. But the other thing you can do is just wait for the rebroadcast to show up in 15 minutes and then just pause on the screen, right? But every single day, I'm going to try and find problems that are online for you that you can use for practice. All right, so please don't forget that I do have a Facebook page. If you don't have Facebook, that's okay. You can still bookmark the Facebook page. I have a big announcement coming next week. It's going to involve me trying to use my Facebook page to post questions for each of the 4 AP Physics exams, 1, 2, Mechanics, and EMAG, that are like little tiny exercises, but are going to be like of the form that you're going to do on your AP exam. So they wouldn't have math. They'd be like writing tasks, right? Because you're going to write only on your AP exam. I'm not sure how I'm going to structure that yet, so I'm not making the official announcement, but just you can either like me if you have a Facebook account, or you can just bookmark the page even if you don't have Facebook. All right, see you next time.